So 2 thank yous first. So first of all, to the organizers. This has been amazing, and I know it was an enormous amount of work, so huge applause for all the organizers. Second, basically everything in this talk I learned from Sam Kappelman-Lyons through the VC1 of the CTC Discord. Those who know, I suppose. So anyway, none of this is original to me or anything, but it's basically just I picked some cool math stuff. So I'm Zetamath, and I'm going to teach you some cool math stuff. That is my hope. I should also preliminarily apologize because I think basically nothing I say is going to help you set puzzles or help you solve puzzles. But it's about puzzles, so we have that. So that is why. Okay, so my talk has 3 pieces that I'm going to tell you about. So the first, I'm going to talk about some graph theory and some applications to Sudoku. And basically the reason I'm going to do this is because I think you basically know everything I'm going to tell you about Sudoku, or at least you'll know most of it. Maybe I'll dip into some constraints you haven't thought of before. But that's meant to be familiar and to introduce you to the language I'm going to use for the rest of things, which is to talk about graphs. Then I'm going to talk about my personal trauma involving Yin-Yang and various things that I learned in doing that. In various complicated ways. And then I'm going to talk about penalty theory, which is this weird way of approaching certain kinds of Heyawake puzzles, which is a kind of pencil puzzle. We'll talk about that. So that's our rough outline. So first, let's talk about graph theory. And so first of all, when I say graph, you probably picture something like the thing on the left, unless you're already in the sort of mathy siesta sphere or whatever. But when I say graph for today, I don't mean the thing on the left, I mean something on the right. And what is on the right, just to clarify, I've got some circles that are in black and some lines connecting them. So basically some dots, which usually get called vertices, some lines that usually get called edges, and we're marking the connections between them. This shows up in a bunch of different areas, and at least my experience is that graph theory is a very, very wide but shallow area, so you can go sort of in infinitely many directions with graph theory. I'm going to try and pick narrow directions because I've only got 90 minutes, so I like to do that. Now, you might ask, what does this have to do with Sudoku? And if I fill in the lines, you might be able to see what this has to do with Sudoku. Namely, what are the lines here? German whispers, right. It is exactly what I've done here. So what the lines here do, I've omitted the digit 5 entirely. We have a long relationship, some of you know. I've drawn lines where there are valid German whispers connections. So that is where things differ by at least 5. And there's not lines otherwise. Okay, so we'll talk about that example and things we do with it later. But before then, I want to get warmed up, have a little game. So here's a graph. It's the graph of a constraint. I could play the same game where I'll press the button and numbers will go in. What constraint is this? Kropke, right. This is white dot. And so if I put that there, you can see if I fill this in, there's a line between every pair of numbers that are adjacent along the line.
Those are clearly black dots.
They're clearly black dots. That is true. That is true. That's clearly black dots. Say it again now. Yeah, so this is black dots. So here, if I fill this in, you can see the 1, 2, 4, 8, and you can see the 3, 6. And I want to point out this picture already tells you an awful lot about all the deductions you make with black dots. So for example, I put 3 black dots in a row. It's got to be from 1, 2, 4, 8. You can see that thread. The 3, 6 is sort of off there in its own island by itself, and everything else, the 5, 7, 9, is off over there. So this graph contains, in some sense of necessity, this graph contains all the information you could know, but actually it makes a lot of the deductions that you're used to with this constraint very clear. Okay, now we'll go into crazier ones. How about this one? XV, wow, that was fast. I thought when I did this, I thought this was going to be take a lot longer. So here I've mooshed together X's and V's, and so you can see this kind of thing. I'll note one thing that you might ask yourself is, can I make a unique puzzle with only X's and V's and no givens in the grid? You can answer that question by this picture, because this picture tells you everything there is to know about X's and V's, and so what you can see from the picture is, well, I could certainly reverse the top and the bottom U-ish shapes, so I definitely can't. right? And so that's one thing that is useful. If I brought my laptop, I would have added this example yesterday during Glum Hippo's talk. Someone from the chat suggested, I think it was Sarah, suggested dots where things either sum to 6 or multiply to 6, and talked about what you could do. First thing I did when people were talking about this, I made the little graph equivalent to that to see, it was sort of 2 length, 3 lines that you could switch. So you could do that sort of thing. What about this one? Difference up to 2, that's exactly right. So this is usually called Chinese whispers. So these are numbers that differ by at most 2. So this is the original whisper, although the one that shows up much less for reasons that maybe will become clear. How about this one? It's the same thing, right? I can guarantee you've heard of this because this is Chinese whispers again. So I want to note here, you naturally as a human who's looking at these things, they're visual representations. It's very easy to read things into the visual representation that are not there. Because the graph only cares about where the dots are and where the lines are, not where you put them. And so things can look very different, even though they're exactly communicating the same information. So just be a little bit careful when you look at pictures of graphs that might look one way. They might not actually be sort of quote-unquote honest. How about this one? Good guess, good guess. Not this time, but this is Dutch whispers, right? So this is difference at most 4. And so the giveaway, if you look at this and are sort of thinking through all of your constraints, there's a little triangle at the bottom, as we'll talk about later, you might recognize with the 159 piece from Dutch Whispers. And we'll talk about that a little bit in a minute. Okay, we've got one more. It's been guessed before. This is parody lines, yes. I was very happy to see that parody lines were over on this poster because that was when I was like, I'm not sure how many people know about parody lines. Like, I like parody lines. It makes a nice picture, but I wasn't sure. But then it was over here a bunch. So I was like, great, people will know parody lines. And so here is a picture, which for some reason I see grabbed the wrong version of the picture for this purpose. So I did not actually map it. But anyway, it's parody lines. Okay. So I want to talk about structures of graphs, and in particular the kinds of structure that are useful to us as solvers. And so here is a better picture, I think, of the German whisper graph. So again, this is the same graph drawn in 2 different ways. I think the way on the right shows you how you probably internally think about German whispers. Namely, it shows you this coloring here, where you've got the low digits, which hopefully are blue, although if you're Simon, they might be red. And then you've got the high digits here in red, and you've got all the connections. And the key thing here, the thing that we're going to come across over and over today, is that all the connections are between blue dots and red dots. There's no connection that connects a blue to a blue or a red to a red. That's called being bipartite. So I'm not going to say many fancy math words today, but one of the fancy math words I'll say is bipartite. And an awful lot of deductions, awful lot of deductions that we make in standard Sudoku constraints could be phrased, not necessarily usefully, by the way, but could be phrased as the statement that there's an underlying bipartite graph that you're looking at. And so just what does being bipartite mean? It means exactly what I just showed you could do with German whispers, which is that I can split the vertices into 2 halves, and all the edges that connect things connect to the 2 halves. Nothing connects within a half, so no blue to blue, no red to red. So here I've gone ahead and picked some of our favorite characters from the talk so far, and so I've split them here into which things are bipartite and which things are not bipartite. Now there's a pattern here you might notice, which is that you see the constraints on the left a lot more than you see the constraints on the right, which I would argue is not a coincidence, because coloring things is fun, and even by definition, you are basically looking at things you can color, basically are the bipartite graphs, and if you can't color it, it's not bipartite. Okay. Now, I wouldn't be a mathematician if I didn't ask why are these things bipartite. So here, for example, here's a proof that the white dot thing is bipartite. And in fact, here I've made the things orange and blue, which I think are their traditional colors because the word odd starts with O, and the word even has 4 letters, which is the same number of letters as the word blue, I guess. I don't know. For some reason or another, it's blue. But you can see this. And again, I just want to point out, the picture on the left doesn't at all make clear whether this graph is bipartite or not. The one on the right does. And so if you're thinking, why is it I so often end up coloring odds and evens? Well, here's a bipartite graph that sort of shows you why you would end up coloring odds and evens very naturally with white dots. And so this neatly encapsulates things like every white dot has 1 odd and 1 even on it that we often use as a step when we're solving some sort of Kropke puzzle. Okay, what's going on with the Dutch whisper graph? Why is that not bipartite? And so the triangle's really the problem, the 5 is really the problem, but basically what do you do? And so the nice thing is it's really easy to decide if a graph is bipartite. You color a vertex, pick a color, it doesn't matter. I've apparently picked purple. Okay, well this 9 that touches that has to be the other color because it touches it. And then immediately we run into this problem that 5 now has to be neither of those colors. And so this graph is not bipartite. Now, interestingly, even though the Dutch whisper graph is not bipartite, almost all the deductions that you make in a Dutch whispers puzzle are about bipartite graphs. And so we've got this triangle here. So I misremembered what my next slide was. We got this triangle here. This is the culprit. And I could just show you. Oh, no. Anyway, the slides are in some order. We'll find out. So what I wanted to point out is if you actually remove these 2 edges, or in fact either of them, you are left with a bipartite graph. And so almost all the deductions you actually see in a Dutch whispers puzzle come down to this observation. So you see something like you see an odd length loop in a Dutch whisper, and you know, there has to be a 5 in there, because if there wasn't, you could ignore the green 5 for Casey over there, and then you'd have a bipartite graph. You couldn't have that because it has to alternate back and forth between these things. And so ultimately, funnily enough, even though the Dutch whispers graph is not bipartite, I think still the structure of it, basically when you're solving it, basically always hinges upon, okay, where are the 5s? What are the 5s doing? Okay. If you believe me that triangles are bad, there are an awful lot of triangles in the Chinese whispers graph. So believing that this is not bipartite, you'll probably pretty rapidly believe if you look at all of these triangles. Okay. Here's a graph that happens to be bipartite that shows up all the time. It's really hard to overstate how often deductions show up about this graph being bipartite. So I want to be very clear, what are the things in this graph that are bipartite? So I have a grid of cells. In this case, I chose a Sudoku grid because I was talking about Sudoku puzzles, but it could be any puzzle type that has a square grid. And so we have all of these, and there's edges connecting cells that are orthogonally adjacent. So if you think how often you have come across the phrase orthogonally adjacent in rules descriptions of a puzzle, basically always that is because they want to have access to this sort of deduction. That is the sort of deduction that comes out of a bipartite graph. Okay, and again, if you wonder, why don't I see puzzles that use orthogonally or diagonally adjacent nearly as often? Well, it's because they're horrible. And the reason why they're horrible is because that graph doesn't have any nice structure like this, or at least the structure is considerably less nice than this structure. Okay. So there are a billion different deductions that you could make based off of this, but I've picked just one for you as an example, which is that if you try and put a closed loop in this grid, it's never going to hit every cell. And the reason for that is that a closed loop is going to need to have an equal number of red cells and blue cells, and that's a problem because this grid has one more red cell than it has blue cells. And so that might not be obvious when you first think about it, that if you actually tried to draw this loop, and you could get an awful lot of the cells in your loop before you realize, oh, I can't get this one, and it might sort of feel like, oh, I just need to change it just a little bit to get it, but you're never going to get it, and this is why. Okay, so that is what I have to say, sort of preparing us to think about these graphs. Okay, so when I was going to make these pictures, especially for this part, I knew I was going to make a lot of pictures. And Ryan's had always been telling me, ChatGPT is really useful for doing things. So I asked ChatGPT to help me with a lot of these pictures. And so I asked it for an example of a completed yin-yang puzzle. This is what it gave me. It was not the most useful. Let's give you a better example here. So here are the rules of yin-yang. And so the convenient thing about yin-yang is that it has only 2 rules. So one of them is that each color has to be orthogonally connected. And so in this case, I've matched the white dots seemingly with yellow and the black dots with purple, but whatever colors you happen to like. And you're not allowed to have any 2x2 be monochromatic. So every 2x2 needs to have both a yellow square and a purple square in it. And so the clues here, so the one on the left is what a blank yin-yang puzzle here would look like. That needs to have, or those clues here in a traditional yin-yang are just markers of what color some cells are. Okay, so there's a couple sort of secret rules of yin-yang. So I think most people sort of internally immediately start thinking of yin-yang as having 4 rules. So here are 2 more rules that yin-yangs have, and if you've done many yin-yang variant Sudoku hybrid puzzles, then you'll probably have thought about both of these. So one of them is that the border cells of each color form one contiguous group. So I've drawn here 2 borders. The one on the left is okay, the one on the right is not okay, is what I'm saying. So when I say this, I'm specifically ruling out the one on the right. And I want to think about why that is, and so I've distilled to you the barest example of what I'm claiming is that this is not possible. No matter what you do, this won't actually be fillable. And the reason why is if I want to try and fill this in, well, I have to connect the yellows in some way, and I've chosen a rather exciting way, if I do say so myself, but this way to fill them. But there's a problem now is that I also have to connect the purples, because by assumption, the purples are also connected to all the purples, but by drawing this, I've severed that possible connection, so we just can't do that. So we always actually have the left side, some version of that, not the right side. Okay, secret rule number 2 is that there are no checkerboards anywhere in the grid. To clarify what I mean by that, I think it's useful to think about the fact that there's 16 ways I can fill a 2x2 with the colors yellow and purple. Okay. One of the rules explicitly is that I don't do the one at the top left and I don't do the one at the bottom right, right? That's what no 2x2s means. But secretly, also you can't do the ones in the other corners either. And so that's not explicitly part of the rules, but it's a consequence of the rules. And the reason why it's a consequence of the rules is actually almost exactly the same as the reason for the border rule, which is that if I just try and put one of these checkerboards, or Battenbergs, as you'll sometimes hear if you're hungry, here, and you say, okay, well, I know I've got to connect the purple to the purple, and so you do that in some, again, gorgeous way that I have chosen, then you now run into the problem that you've just made it impossible now to connect the yellow to the yellow. Okay. I'll note a lot of different pencil puzzle genres have some sort of no checkerboard rule, like Cave also. It depends on exactly what the rules are, but in this case, it's actually, I think Yin-Yang is the one where it's the easiest because the 2 colors are symmetrical and you don't have to think about what exactly it is that you're doing. Okay. Here I have put a slide which I've just called the vibe check on the yin-yang genre. So I went on Puzzlink, and so Puzzlink went down for a bit, so I had to go back to 2022 before I had a whole year of data. So if you're not familiar with Puzzlink, it collects pencil puzzles, lots and lots of pencil puzzles in lots and lots of genres. And so if you ask Sudoku people to name pencil puzzle genres, I bet yin-yang would be very high on the list. However, on Puzzlink, there were a total of 6 posted. Now, I tried for comparison to count any other genre, but I got bored before I got to the end of clicking all the pages of, like, Heyawake, and I was like, I bet there can't be that many philomenoes. No one likes doing vanilla philomenoes, right? But there were still hundreds, if not thousands, of vanilla philomenoes posted in 2022. Now, in the same year, there were 43 yin-yangs posted on LMD, most of which are Sudoku hybrids. And so a question you might ask is, why don't people set more yin-yang puzzles? And maybe you could say, why do people on LMD like yin-yang puzzles more than people on puzzling? Because there are at least an order of magnitude fewer puzzles posted on LMD than there are on Puzzlink. But nonetheless, we have this thing. And I think the reason is very simple. Puzzlink is mostly populated by people who set a bunch of puzzles. And no human has ever set more than one yin-yang puzzle. Because you set one, and you find out very quickly just how much the puzzles break. And so that's actually how the sad story of how I came to be standing here, intro to a movie cue, I suppose, how I came to be standing here at this moment talking about yin-yang things is I started a yin-yang puzzle, and I was going to make this puzzle. It eventually worked. It was called Baby Dragon. It was a yin-yang 10-line puzzle. And I put in one clue in the grid to get it started, filling in the border. And then I spent a week of my life trying all sorts of different variations, and it always broke at the end. And it turned out that literally from the first clue I put in the grid, it was already broken. Because there is a rule that is not obvious about what the borders of yin-yang grids that are filled have to look like. And I had put something on the border, and so that ended up working out this way. So just to show you, here's one example. One of these has a solution, one of these doesn't. You could take a pic. This is, if you're looking at them trying to think they're exactly the same, one is 10 by 10, one is 11 by 11. You'd always be wise betting on even and odd being the distinction. And probably, actually, it's not that hard to figure out that one of these has a solution that you could just draw in your mind, depending on how good you are at visualizing these things. And then one of them doesn't, and that's weird.
One has many solutions.
Yeah, one has many. Yeah, sorry, yes, one has many solutions. Yes, correct. But if, in case this isn't enough to upset you, this is a grid that has no solutions, which is, again, quite upsetting, at least to me, that this works. So anyway, I'm going to try and explain to you why this works. But this is the kind of thing that when you're setting, unless you're aware of this at the back of your mind, you can very easily get yourself bit by these kinds of things because there's this weird global condition that you might not be aware of that's not so different from starting by making a puzzle and saying, this is a 9 by 9 grid where I want you to make a loop that visits all the cells, which, as we learned earlier, is not possible, but it's not sort of easy to see why. And locally, you can get very far in making such a puzzle, and then you always get bit at the end. Okay, so I'm going to try and explain this. I'll note, by the way, I strongly discourage anyone from using any of the deductions I'm about to teach you as steps in puzzles. At least personally, I don't like basically undiscoverable things. However, if you're setting a yin-yang, if you're setting your 1 for your life, if you decided that's the time that you're at, then it is worth knowing these things for your own sanity to make sure that you don't break the grid. So at least this will be a good start towards that. Okay, so in order to do anything in today's talk, I have to convert everything into a graph. And so the graph I'm going to convert everything into here is slightly different than the graph that I converted things into before. So here the dots are not the cells, the dots are the intersections. So now actually the lines, well, conveniently, here's the nice thing, the lines are already there. So here's the puzzle, here's the graph. And so we've got an edge here connecting each of these dots that are adjacent. Note, by the way, the size of this in terms of the number of dots is 1 more than the size and the number of squares, right? So this is 5 by 5 as a grid of squares. It's 6 by 6 as a grid of dots. Oops, I think I skipped a slide there. So this actually all comes back to loops. Even though you might not think of yin-yang as a loop genre. I mean, I probably hope you don't think of yin-yang as a loop genre, actually. But in fact, actually, any yin-yang you take, if you take the boundary of the white cells, then you get a loop. And it has to be a single loop, with one exception that I'll let you people who are correcting me in your head figure out. And you could do exactly the same thing. I get a few thumbs up from people who are like, I was already prepared to come up to the mic and give you the comment. So Sorry for ruining your moment. So we have these two loops. And so what we can actually do is we can actually think a little bit about these loops and what's going to be true about these loops. Now, here's again just drawing this in with a graph for you so you can see that these things are actually loops. They're in the graphs. Yeah?
The two loops either share a boundary or outside, right?
Yeah, so yes, if the one exception, yes, that if the outside is entirely one color, then you end up with two loops. Okay, so perhaps unsurprising, I mentioned earlier that this was basically the most important graph I was going to talk about. Here it is again, basically, although it's shifted arguably a little bit, because it's shifted from the centers to the corners. But the graph is bipartite. And everything weird about yin-yang borders comes down to this observation that this graph in which this loop lives is bipartite. And so, as we noted earlier, loops in bipartite graphs have to have even length because the colors alternate back and forth. And so you could even say, even better than they have even length, they have to have an equal number of, in this case, yellows and greens. I didn't really have any aesthetic as I went through this guessing what colors I'd pick. So anyway, enjoy the assorted colors that you get as we go through this. But basically, we need to make sure that every boundary, that is the loop, remember the loop is the boundary, needs to have an even number, an equal number of yellow and green dots. Okay, and that's going to be a problem once I tell you one other thing, or once you notice one other thing, if I highlight what the cells are that are actually on the boundary. And so if you squint at this for a little bit, you'll notice something, and if you play around with this, you'll notice something in particular about where all the red dots are and where all the blue dots are, or vice versa, where there's always a red dot and where there's always a blue dot, which is, in fact, in the entire interior of the grid, there are both red dots and blue dots. So I've gone ahead and circled those for you in case you don't know what I mean by dots on the interior of the grid, just to show you, hey, there's red dots and blue dots in all of those places. Okay. Now, I could just claim this, but you could ask, and it would be a perfectly valid question, why? And the answer, at least to me, is quite beautiful. Namely, you can go back to thinking about the 16 ways that you could arrange two cells of each color in a 2x2, here they are, and which of these things could be the shape of an inner vertex not on a boundary? Well, the only ones of these that would not be on a boundary are the one at the top left and the one on the bottom right. All of the others are on the boundary between yellow and purple. Even including the two that aren't possible, which would have other problems if you had the checkerboards. You could give an alternate proof of the no checkerboard thing that involves loops, which would be considerably worse than the standard proof. But you could, it's possible. I'm a mathematician, I'm supposed to care about these things. So, in fact, and this to me, this is the nugget that makes this so cool, like this is why I really love this, is that it's exactly the rule that there's no 2x2s, that somehow dictates that there's no vertex that's missed on the inside of the grid. Almost surgical precision to guarantee that that rule guarantees that this weird deduction happens. And I'd really love to know, I don't know, but I'd love to know if this was known and deliberate when this genre was designed or not. I suspect it's a coincidence, but I don't know. I have no idea. So if anyone knows, if whoever invented Yin-Yang, who may not be my best friend after this talk, but if anyone knows, I'd be very curious if that was known and deliberate, because it is exactly that consequence we're interested in. So once you have that, it's actually not that difficult to write down plenty of examples of borders that are not possible. So here's a border that is not possible for any yin-yang grid. So in other words, I'm claiming there's no way that you could fill in the center cells. And it could be much bigger, but I wanted you to have a fighting chance of counting. So on the inside, if I think about what this is going to look like, and let's just think about purple, because I like purple better than yellow, I suppose. So on the inside, sorry to the yellow fans, there are 16 interior vertices here, because it's 4 by 4. And then if I count the outside, it's, and you can see my cursor, right? Yes, it's 1, 2, 3, 4, 5, 6, 7. 16 plus 7 sounds like 23, which has the significant problem that it's odd. And so I cannot possibly finish this grid in a way that will let me have an even border around this. So it's always going to break if I try and fill this in. Okay. So that already is enough to tell you, I think, why people tend to set one yin-yang, is because this is a really not obvious problem, at least to me. Even after I believed I thought that it was a problem. In fact, what I did when I kept breaking this puzzle for a week is I messaged KNT, who I thought was the person who would most likely know. And KNT is like, oh yeah, there is some weird thing with a border. Here's a series of screenshots of Sam Kapelman lines talking about it in VC1 that I kept in my folder or whatever. So anyway, so that's how I learned about this in that particular instance. Okay, so basically, if you want to know if a border is possible, the first check is count how many vertices that theoretical loop would have, and if that loop would end up having an odd number of vertices, that's a significant barrier, namely it makes it impossible. Okay, so earlier I gave you this example where I said that one of these grids was impossible, so here's an example where it's impossible. And here's where you really have to realize that I blatantly lied when I said it's always going to be one loop. It's in fact 2 loops in this instance that are going to be the border of the black cells. However, the interior loop is going to have to visit all 81 of these vertices. And you might recall earlier a discussion about how it was very difficult to visit all 81 vertices of this 9 by 9 graph, and so this is not possible. So this is an example. It's not possible. And you can figure out that this exactly happens in the case that your grid is even by even. And so, in fact, as we'll see in a moment, it's the even by even yin-yangs that have the most pathological requirements because there end up being an odd number of vertices in the center. So I think we're phenomenally lucky as a group of more Sudoku people that 9 is odd. And so the 9 by 9 yin-yang puzzles don't have yet another hidden secret rule that is even more hidden and more secret, and that I would very much not wish to explain every time I do a yin-yang puzzle on my stream, for example. So here we go. So in even by even yin-yangs, there's always a multicolor border. That's really your takeaway here. And so I've actually had a few people tell me over the years, oh, well, some yin-yang puzzles just have an added rule that the border has to be multicolor. And I think what actually happened is that a lot of people have internalized this fact as a rule rather than as a thing that they think about, at least as far as I've seen. Okay. Whereas in this instance, so here's my attempt, very noble attempt to finish this. And note it didn't work, of course, because there's a 2 by 2 here. But if you think about what we actually proved something even stronger than what I claimed, which is we actually claimed that if you forget one of the rules of yin-yang, if you forget about the no 2 by 2s rule, so in other words, if you make the rules of yin-yang one rule, which is that the yellow are connected and the purple are connected, well then the parity of the number of 2 by 2s is going to match this parity. So in this case, what we actually proved is that there's going to end up being, in this instance, an odd number of monocolored 2 by 2s. And so that's the actual fact. This lurking around here is if you try and complete this, you're going to end up with an odd number of 2 by 2s, which is a problem in that 0 is not odd. And so that does not end up working. Okay, so that is a pretty cool thing. But we can do even more, actually, again, in the specific case that we're looking at an even by even grid. So here I've put an even by even grid here. And the thing I want to point out to you, and this showed up earlier, actually, in the 9 by 9 example that I gave you, which is that there's not the same number of yellow and green dots. And this is owing to the fact that, remember, the grid of squares and the grid of dots are off by 1 in size. So it's the even by even case is the only case where you end up with an odd number of total dots, because you add 1 to both evens and then get an odd times an odd, which is slightly tricky to keep track of. But that is what's happening. So if you're thinking it's weird that it's the even by even case that's the broken one, it's actually the odd by odd case, but it's the odd by odd case on the number of vertices, which then is the even by even on the number of squares. Okay, so what happens then? Well, we know any yin-yang puzzle in this grid, we know the border has to visit all of the yellow and green cells on the inside, and then some more, right? That's what we've just proved, is that we need more, because that's an odd number in total. But actually, I've gone ahead and counted for you. That's 41 yellows and 40 greens. That actually means that when I go to add stuff on the border, I need to add stuff on the border in a way that balances that out, because the border needs to have an equal number of yellows and greens. And so when I take all the cells or all the corners I have to take, all of these, I'm at 1 more yellow than green. So I need to choose border cells that get me 1 more green than yellow. And if you look at what that means, if you sort of think about where on the border I'm going to take, that means along the border, I need to start and end at a green vertex. Because if I start at a green and end at a yellow, then I've got an equal number of greens and yellows. And if I start at a yellow and end at a yellow, that's even worse. Now I've got an extra yellow over the number of greens. Okay. And so what that means, when you actually look at it, is that actually every even by even yin-yang puzzle has a bajillion starting pencil marks. Namely, all of the cells that I have dashed, they all have to be the same color, as in each pair has to be the same color. And the reason for that is that, for example, if these two aren't the same color, then that means that this yellow vertex is the edge of my border cells, and then I end up with not 1 more green cell than yellow cell around the border. Okay. So here's why I said we're very lucky that 9 is odd. Because all of our hybrid Sudoku puzzles, we don't have to worry about explaining this at the beginning of each puzzle, which is probably especially lucky for Simon, who really does explain every time what's happening. And I don't think Simon would enjoy having to explain this picture every time. Okay, so that's yin-yang. Next, I want to talk about Heyawake, which has the disadvantage over yin-yang that it has considerably more rules, twice as many, in fact. So I'll show you an example, but I couldn't fit the example and the rules on the same slide. Sorry. So we're going to shade some cells in a grid. You'll see a grid in a moment. The unshaded cells need to be connected, so that should sound a little familiar at least. And if a region contains a number, that's the number of shaded cells. And now there's this last rule that's really hard to wrap your brain around until you have seen it a number of times and thought about it. Exactly what it means is what I call the border rule. Here's the good news. None of the math I'm going to do involves the border rule at all, so if you just want to pretend that I didn't say that, it doesn't actually have any impact on penalty theory at all. And in fact, actually, there's sort of a name that I'm told people use for puzzles that just meet the first 3 rules, which is that these are often called dynasty puzzles. And then some other puzzles meet these requirements, like Yajlin, I suppose, is another one. And there are others that say that kind of thing, where you could have a similar statement. But the last rule, just so that we say it, and I'll use it later, is that if you take an unbroken string of unshaded cells, that can't ever cross more than 1 border. And it has to be a string either horizontal or vertical. No diagonals, no turning or anything like that. But it can't ever cross more than 1 border. Okay, so here, just in case you have never seen this before and are having trouble visualizing this, here's what a completed Heyawake grid looks like. So puzzle on the left, solution on the right. And so you can see, for example, this 0 is saying there's 0 shaded cells in this rectangle. So in fact, there are 0 shaded cells in the rectangle. And that weird border rule, if you want to visualize it, I think a good way to think about it is in terms of these 3 cells. That's a string of 3 consecutive green cells, and it crosses 1 border. If this cell were green, that would be it crossing two borders, and you're not allowed to do that. Likewise, if this cell were green, it would be crossing two borders if it went that way. Okay, so that's the rule. You can verify for yourself that all the green cells here end up connected, I hope. I admit I didn't check this too closely. Hopefully it's true. All the green cells end up connected, and all of the regions have the claimed number of shaded cells. So that's what we're thinking about when we think about a Heyawake puzzle. Okay. So how are we going to turn this into a graph? Okay, and so as always, there's an exciting new answer for each of these. So we're going to turn this into a graph by taking just the unshaded cells and then drawing edges between them when they're connected. So here's my picture of what this graph ends up looking like. And so again, where are the edges? The edges are exactly between the orthogonally adjacent cells that are not shaded. So the pressure here, the thing we're going to be interested in thinking about that's going to lead to the questions that are going to lead you to think about penalty theory is, what are the consequences of the fact that the graph has to be connected? In other words, I have to be able to get from any vertex to any other vertex, because that is one of the rules of Heyawake. And so I should say, by the way, my goal here, I am by no means a penalty theory expert. My goal is basically to teach you the set of questions that you would ask that would lead to you figuring out the formulas, and enough that if you are so inclined, you can sort of be calculating the formulas as we go along. So here's the question that you can ask. So how many edges does it take to connect n vertices? How many vertices I have? How many edges do I need to have? And the answer, it turns out, here is not hard. It's n minus 1 is the minimum that you need. And so we get this statement here that for any grid, or for any valid Heyawake grid, we need the number of edges present in the grid to be greater than or equal to the number of unshaded cells minus 1. This is not a very strict bound most of the time. So here what I'm claiming, if you look at it, is that 37 needs to be larger than 28, which it definitely is, and there's a lot of wiggle room still left. Okay. Penalty theory is going to tell you absolutely nothing if you have that much wiggle room left. It's going to turn out to be much more interesting when you are sort of right up against the wall. But I want to justify, why is it that you need n minus 1 edges? Why wouldn't n minus 2 do? And so I think this makes the most sense if you think about it in terms of those little toys that you make models out of. And so I guess if you're a chemist, the things that you make models of atoms out of, where you start with a bunch of atoms, say n atoms, and then you're going to connect them. Well, each piece you do, what are you going to do? Well, you're going to connect two pieces, or you're going to just throw in an edge that doesn't connect two pieces. And if you throw in an edge that doesn't connect two pieces, well, you've not gone down from having however many pieces you had to one fewer, or you do, in which case, how many times do I have to go, or how many times do I have to drop from n pieces to n minus 1 to n minus 2 to n minus 3? I have to drop n minus 1 total times in order to put this together. Okay, so that is sort of the goal here. Okay, so here I've shown you a tighter example of what this looks like. So here I actually hit the bound. So again, just to remind you, what is the bound? The bound is that the number of edges always needs to be at least as big as the number of unshaded cells minus 1. Or I guess I could have said that as the number of edges is strictly greater than the number of unshaded cells. That might have been better. But here I've counted, and again, I've sort of tried to do the counting for you. And we end up with this. Now, it's worth noting the structure of the graph here when we have this actual minimal thing. So I had debated whether I was going to say the word tree or not during this talk, but then last night, randomly at dinner, Ranks said the word tree in this context, so I had to point out, in this particular instance, when we exactly meet the bound, that's when this graph ends up being a tree, and what does that mean? That means if I remove any edge, it disconnects the graph. Every edge is necessary in order for this graph to stay connected. So how am I going to conceptualize what's happening here? And so I'll warn you, if you go looking up penalty theory for the purposes of using it, you're going to see a bajillion formulas that float around that basically have to do with, if I have an m by n grid, what do all of these numbers that I keep flashing on the screen and counting for you so you don't have to count them, what do they all end up being in these various instances? I'll try not to torture you too much with that. But here, let's start with a blank grid, and let's think about adding shaded cells to it. What happens? Okay, so let's just start with a 6 by 6 blank grid, 0 shaded cells. So there's 36 unshaded cells. There's 60 edges. What is my statement then? My statement is 60 is bigger than or equal to 35. Thumbs up, that's definitely true. I think for Sudoku people, I think the best way to think about this is that is 25 degrees of freedom. Is I think the way that you can think about this. I've got 25 more edges than I technically need to meet the prompt, which is that I need all the green cells to end up being connected. Okay. So I've got a lot of wiggle room at the moment, and basically what we have to think about is how does that wiggle room go down as I shade cells in the grid? So here, by the way, just to show you some of the things I'm not going to say, here are the sorts of formulas you'll see when you try and do the same calculations, but with an m by n grid. It's not so much difficult, so much as messy, if you want to go through and do all of these, but I won't make you look at that. So what does happen when you shade a cell? And so one thing you realize rather rapidly, and this is why there's a lot of mess in penalty theory, is there's actually 3 kinds of cells that you can shade. You can shade a cell on the inside, you can shade a cell on the border, or you can shade a cell in a corner. Okay. And so you have to think of what do each of those things do to the number of edges and to the number of unshaded cells, minus 1. Okay, well, if I shade one in the center, like this one, I'm throwing out one vertex, that is one unshaded cell, so this number is going down by 1, but this number is going down by 3. Right? By 4. 4 is 4. Anyway, if I remove 4 things, that number goes down by 4, right? If I remove this, then that number goes down by 1, and that number goes down by 3. And if I remove a corner, this number goes down, this number goes down by 2, the number of edges, but the number of unshaded cells, that number goes down by 1. It's always going down by 1 if I shade one cell. Okay. Now, here's the thing that you might or might not think about as I try and pace. I've been so good about staying right here. Okay. How do I know that's always going to be true? What if I shade a cell next to a shaded cell and I've already removed that vertex? Okay. But very conveniently, the rules say you can't do that. So you don't have to worry about that particular instance. And so because you can't put shaded cells next to shaded cells, you always remove 2, 3, or 4 edges based on the 3 cases, which are the corners, the borders, and the interior. And so I think it's actually most useful to think about what this does to that degrees of freedom number that I mentioned back here, is that the degrees of freedom is the number of edges minus this bound. Well, if you shade something in the center, that number has gone down by 3 total, because I subtracted 1 from this side and 4 from this side, so that number has gone down by 3. And then it goes down by 2 in this instance and by 1 in this instance. So if you see the 1, 2, 3, if you look at penalty theory, you'll see these 1, 2, 3 numbers associated with corners, borders, and center cells. That's where the 1, 2, and 3 come from, is those are the number of degrees of freedom that are consumed. Okay. In fact, you're always consuming degrees of freedom. You can't shade anything without consuming degrees of freedom, but it costs you more to shade stuff inside the grid than it does to shade stuff in the corner or outside the grid. Okay. So here's the sort of punchline, just to say this again, that we should sort of keep in mind that we have sort of a price, if you want, of what does shading a corner cost. It costs 1 degree of freedom. Shading a border costs 2 degrees of freedom. Shading an inner cell costs 3 degrees of freedom. And hopefully we're on the page about where those numbers came from. Okay, so let's do an example with just that. So here's an example. Technically, this is a Heyawake puzzle, but I'm never once going to use the Heyawake rule for it, so I might as well just call it a dynasty puzzle. In other words, just forget the border rule and just think about the first three. And so here, I, as the constructor of this puzzle, have been incredibly kind in that I have put a region that tells you how many interior cells there are, puts a thing on a border, and a thing in a corner, so we can do these calculations. Okay, so basically I've told you that, because one cell out of those cells is shaded, and so on. Okay, and so let's start with what are the stats of the blank grid. So now I've switched it to 7 by 7, so again, you have to sort of recalculate these things. But that means for the blank grid, there's 49 blank cells, 84 edges, and so the number of degrees of freedom is 36, which is that calculation. Okay. How many degrees of freedom do we lose just from the clued cells? And so we said corners cost us 1, borders cost us 2, and center pieces cost us 3. And so here it is worked out, and so this is exactly the case where penalty theory thrives the most. We've used all 36 degrees of freedom. That's what you hope to do anytime you do this calculation. If you're actually solving a puzzle, you hope to find that you've actually consumed every single degree of freedom. And so what that means is I can't shade any cells other than the ones that are already indicated by the clues. So in particular, I can't shade any of these cells because it would cost me a degree of freedom, at least, that I don't have. Likewise, I can't shade any of these cells because that would cost me 1, 2, or 3 degrees of freedom that I, again, don't have. And so when I actually look at this, I have this sort of immediately filled in. But here's where it pays to remember also, what did it mean when this bound was exact? Yes. Right, exactly. So it means now the graph doesn't have any cycles because there's no unnecessary edges, right? If I could remove an edge, then I wouldn't be at the bound. And so I need to avoid having any cycles. So in other words, in this completed grid, there's no way this cell can be green, because if there was, that would be a little cycle of 4 edges that I could trace around here, and that would be at least one edge that I could remove while keeping the green connected. And again, because I've exactly met the bound, there are no edges that I can remove while keeping the graph connected. So here's my picture of what I should have done instead of doing it with the mouse. So here's pictures of those little loops. All of those give us shaded cells now because of this. Okay, and so this is the power, by the way, of penalty theory, is that once you sort of understand this, once you've met this bound, then you get sort of all these kinds of deductions that are open that are just not Heyawake deductions. They're weird other universe deductions that involve things like loops in green cells and other sorts of things. I think there's actually probably room for a genre, and maybe there is a genre and I don't know, that actually just explicitly starts with you shade some cells so that the green cells are connected and there's no loops in green, that maybe sort of skips this whole thing. But that is this. So now there's plenty more cells that would make a loop in green. So it doesn't have to be a little loop, it could be a big loop too. So something like that, I can't have that either. And so I can shade lots more cells here. And so then I end up somewhere like there, and then you just look at more cells, and voila, you end up at your solution here using this idea that it needs to be a tree, ultimately, is my point. Okay. And so here's your solution to this puzzle. Okay. Now, almost never are puzzle creators so kind as to give you clues that look like this. And again, just to say, why was this abnormally kind? It might not look abnormally kind at first. It's abnormally kind because all of the clues that I gave, I told you whether they were central cells, border cells, or corner cells, so we knew their exact cost in degrees of freedom. And so the degree of freedom cost is 1, 2, or 3. Well, here we were able to do all of our calculations, and it all worked out exactly because of this. If we end up with a border if we end up with a border that touches this, then it's worse. So I'm going to show you a little bit about how that goes as well. Okay, and I'm going to slowly shift my view until what we're actually saying here becomes penalty theory, because so far I haven't actually told you what a penalty is or anything of that sort. So I'm going to shift the view here, and I'm going to say that we have a shaded cell shop with a rather gruff shopkeeper who refuses to sell you a shaded cell for any less than 3 degrees of freedom, because he doesn't know what you're going to do with it. But he'll send you a rebate by mail if you put it in one of the indicated places. So if you put it in the corner, you'll get a rebate for 2 degrees of freedom that you can spend later. And if you put it on a border, you'll get a rebate for 1 degree of freedom. Okay. This kind of makes sense for the shopkeeper. You gotta protect your degrees of freedom. But also most cells, if you think about it in a rectangular grid, most of them are in the center anyway, right? There's only a few, literally 4 in the corner, and there's only a few on the border relatively to that. So, it just makes sense, right? So this has the huge benefit that now I know what shading a cell costs. And so when I look at a clue, I can say, okay, here's the cost. Okay. So here's an example. This is by Chaotic Puzzles, who has a very nice Twitter thread writing up all of this stuff here. And so here, Chaotic Puzzles has been considerably less kind than I was in the previous example. And so you'll notice this 18 is a clue for basically the whole puzzle. And it doesn't indicate at all anything about centers or anything of that sort. So you've just got to figure this out. Okay. So if you go ahead and do our calculation, for the blank grid, there's 42 degrees of freedom. And then you look at the clues, and so if you adopt this view, that I'm just going to charge you 3 degrees of freedom, a flat rate for every shaded thing, then I go ahead and I compute this 19 times 3 number, I subtract this, lots of math that I could not do in my head and won't pretend I could, which is why I made the slides, then you'll see that you come out 15 degrees of freedom in the whole, which isn't going to work. It means you need to get rebates of at least 15 points, because I need at least 1 or at least 0 degrees of freedom. I can't have a negative number of degrees of freedom. Okay. Which then leads us to the question, well, what's the maximum rebate I could possibly get? Okay, and at this point, we're most of the way to actual penalty theory, but I'll do an example where I show you the actual way that they think about it in a second. So to figure out the maximum rebate you could possibly get, you have to think about corners, and then you have to think about border cells. And so I've made this colorful because I like colors, but also because I think I've made it so that it is clear that in each of these yellow or red pieces, I can shade at most 1 cell. So if I think about corner cells, well, that's the easiest part of penalty theory. The maximum number of corner cells I can shade is 4, which would be a rebate of 8. Because each corner cell, again, gives you a rebate of 2. I know this nomenclature is complicated, but remember, a corner cell sort of costs you 1, but you paid 3, so you get a rebate of 2. That's where that number is coming from. And so that's a maximum of 8. And then in terms of border cells, well, you've got one region here, the yellow one and the red one, and then that yellow one and that red one, that yellow one and that red one, and that yellow one and that red one. And in total, that is 8. The rebate, again, for a border cell is 1. So your maximum corner rebate here is 8. Your maximum border rebate is 8. So that means the maximum rebate you could possibly get is 16, ignoring everything about the puzzle, right? Not including the clue or anything like that. So the maximum rebate you can possibly get is 16. So we need to get all but 1 rebate. Okay. And so this is how penalty theory puzzles usually work. You usually end up figuring out that, in fact, you need to spend that, or you need to sort of spend that 1 extra rebate, and then we'll get back to where we were before. But note, we're not at no cycles yet, because we still have this. Okay, so here is this piece. Okay. So if I don't shade row 1, column 1, and I've put the proof there on the left, so that you can see this. If I don't shade row 1, column 1, that costs me a flat 2 rebates to not do, right? Because I could get 2 by shading this, otherwise I don't get it. Well, I can't not take a 2 rebate. And this is, by the way, this is because this cell and this cell are already known to be green. I could only cost myself one rebate if I shaded, say, this cell instead in the abstract, if I ignored all of the rest of what's going on. But here, those by the clue are both green, so I have to shade that. So anyway, so you shade that, and you end up over here. And now you notice something. Namely, you notice that by greening this cell, I've now actually cost myself one of the rebates I theoretically could have had, right? I theoretically, when I maxed it out to the 16, I was counting myself as shading this cell, which I've now said, nope, I'm not shading that cell. There's no way to do it. Breaks the puzzle. So now that means I actually need every other rebate. So what does that mean? That means I need every corner shaded, and it means that I need every one of these border ominoes that I have made to have a shaded cell in it. And it means then I can't have, so then we've got all of this like that. So all of that sort of comes in for free. And this is the beauty of penalty theory, is usually when you hit this point, you get tons of stuff. Basically, it just all goes in because you've hit some sort of bound. Okay. Now, we have 0 degrees of freedom, and remember 0 degrees of freedom, because we've already spent our 1, means I can't have any unnecessary edges. And so you can go through and play our same game of looking for loops and things like this. You can even remember that secret rule of Heyawake that I said I wasn't going to talk about much, but here it applies. For example, I can't leave that cell unshaded, or I've got a string of unshaded cells. And if you want to completely finish this, then you have to play this cute little game at the bottom left corner here where you say, okay, I need 3 shaded cells total, just because of the 18 clue, not for any other reason. And I've made a purple group, a red group, and a yellow group that can each have at most 1 shaded cell, because if I put 2 shaded cells in them, I'd disconnect the grid. Or put 2 shaded cells next to each other, both of which would be bad. Okay, so that is sort of the core logic of how this works. These are the questions you can ask to get yourself to where are all these formulas coming from, what are the numbers I'm looking at. It's not the way that makes your life easiest if you're trying to actually apply this, which is where the notion of a penalty comes in. So here's the final reframing of this. And so here it is. Rather than giving you a budget, as I've been thinking about so far, where I just hand you the degrees of freedom, I'm actually going to hand you all the money up front, the degrees of freedom and the maximum possible rebate. So that has the advantage that now I'm only ever spending money or whatever currency this is in Puzzlelandia. So I hand you all of that, and then every time you shade a cell, you just pay me back 3. Flat 3, doesn't matter which cell it is. However, if you leave a corner unshaded, you also have to pay for that, because I already gave you the rebate for shading the corner, and so you have to pay me back for it. So if you shade something but you don't shade a corner, that costs you 1. And if you have a border omino, and by border omino I mean these yellow-red things, one of those border ominoes, if you don't put a shaded cell in it, that costs you 1 as well, because I've already given you the rebate, assuming that you put a shaded cell in there. And also, if you have any extra edges, that is, if you have any edges that are not needed to connect all the unshaded cells, that also costs you 1. Okay. And now, actually, and it's almost a tautology if you dig in deep enough, your budget has to exactly equal what you spend in any puzzle. Because, well, the bound we gave before, if you think about it, where we talked about the number of edges versus the number of vertices in order for it to connect, basically counted extra edges. So everything that we don't spend in anything else almost definitionally goes towards an extra edge. Okay, so if you want to think about this, the nice thing here also is that any grid, you can calculate your budget, and it doesn't have anything to do with the puzzle at all. So if you decide I'm going to do puzzles on an 8x8 grid, you only have to do this calculation once. Or if you love this friendly looking formula down here, you can do that. but I'm not going to justify where it comes from, but if you are motivated to do so, I have full confidence that you can also figure out where it comes from. But here, if I look at this, for this 8x8 grid, I can compute the degrees of freedom as we've done, compute the maximum rebate by counting corners, of which there are 4, and dominoes, I suppose I should say, around the border, so that there are 16, and add those, subtract 1, and that gives me my budget of 65. Does it? Well, I'm going to believe it, even though those numbers visibly don't add to 65. What on earth did I? Who knows? I believe the 65 more than I believe any of the other numbers here, but wondering. Okay, so anyway, so here's a final example, which is a pretty terrible example, but I'm just going to try and show you what this looks like sort of in visceral practice. So we've got a budget that we're going to believe is 65, even though I kind of just told you it wasn't, but whatever. We'll go with it. A budget is 65, and if you look at the grid, you add all the clues, that means we'll see if this is right. 7 plus 4 plus 9, that sounds like 20. I think it is actually 20 shaded cells that I've told you about, right? There might be others. I mean, in this case, literally the only one that could be is this one, but that's 20 shaded cells that I've told you are in the grid. And also, actually, I've told you a few other things that are actually going to cost us money, right? This 20 shaded cells, that's going to cost us 60 right there. So we've already blown most of our budget, but we've got sort of 5 puzzle bucks left over. But this 0 up here is really costly because the 0 actually represents a few things. One, I didn't shade this corner, right? And I was supposed to do that. That cost me 1. But also this little triomino around here, I also didn't put a shaded cell in there. That costs me 1. And then also, there's definitely a loop in this yellow region. So in fact, there's some extra unnecessary edges in here. In fact, there's 2 unnecessary edges. If you just draw your little graph there, there's 2 edges I could snip out of it and then have those. And so if you count just those things that I've said so far, that adds up to 64 of your budget of 65 that you have spent. Okay, and so then you can say, okay, well, I then definitely can't shade this random cell because that would cost me 3 and I've only got $1 left. And so you can unshade that. You could remember the rules of Heyawake, which I didn't when I was setting this. To shade this cell, you could remember like anything about solving Heyawake at all and unshade lots of cells, but let's not do that. Instead, I just want to note that if I think about where my budget comes from, I can't possibly put 2 shaded cells in these 2 ominoes. And why is that? Well, if I try and put 2 shaded cells in those ominoes, which I've here dashed just to show you where the border ominoes were, I'd have to shade these 2, and that would break the secret rule of Heyawake. I'd end up with that. And so here's sort of the fullest version of what this ends up looking like is I know I spent my degree of freedom in one of 2 places, I'm not sure where, but it's spent, and it's going in one of those 2 places, so I can't spend it anywhere else. Okay. And the reason why I like this sort of degrees of freedom view for Sudoku people is we're sort of used to thinking about this with, like, heaven forbid, a little killer puzzle or something, where you're often thinking about these exact terms of, hey, I know I have to have spent this. Penalty theory is really doing the same thing with this sort of budgeted idea. Okay, so that means, again, once you know that, well, you can't spend money on anything else, right? So there's no unshaded corners, no empty ominoes, etc. So that actually gets you to something like here, where you can eventually finish this puzzle. So that is penalty theory, a very rough introduction where you can sort of figure out the details, enough to sort of figure it out, because again, when you read a description of it, at least for me, it sort of involves all these formulas and it's not clear where things came from. I think if you followed this, you could derive all of the formulas and then it will at least seem less cryptic, at least in my opinion. All right, so that means I've promised to do all 3 things that I have I've done all 3 things that I've promised I would do. So Zach will take questions now, if you have any. Also, I should plug that I have a puzzle stream, which is youtube.com/ZetamathDoesPuzzles. And I also have a math YouTube channel where I have sort of hour-long expositional videos about math stuff, which is just youtube.com/Zetamath, which is why I ended up with the Sutter name Zetamath in the first place, is because that was sort of where I started. All right, questions?
Very excellent talk. Thank you very much. I think that my squirrel brain has one question for you, which is, can you just give us the quick breakdown of what are the ominoes definitions, which I believe are you always have a triomino in all the corners, and then depending on whether it's even or odd, you can only then have dominoes or single shameominoes, monominoes, right?
This is a great question. This is a great question and a great point for me to admit that I blatantly cheated here. As you say, I could have monominoes or dominoes. And so I could have actually put this monomino or this domino in any order, and it would have worked out just fine. But I put it in this order so that I could then say, oh, look, oops, we shaded row 3, column 1. That cost us our degree of freedom. Really, yes, exactly what you're saying is right. You can put a monomino and a domino to handle the even-odd case, but you could put the monomino anywhere along there. So that's exactly what it is. No domino can have two things. The triomino's at the corner because of connectedness. If I try and put two things in there, it would have to go in these corners, and it would disconnect it. And then you can stack these monominos and dominoes however you want down the sides.
I guess my question is, you can only have monominoes, dominoes, and triominoes.
Correct.
And the triominoes only exist on the corners.
Correct. The triominoes only go in the corners, and then you use as many dominoes as you can everywhere else. And then if you've finished, done. And if you have not finished, then you stick a single monomino to handle your odd case.
Would it be more accurate to say that in a odd length, it's to maintain full degrees of freedom, there are specific cells that have to be shaded?
That would be another way to say it. Or like internally for me, I think it makes the most sense actually to say this thing is a triomino, but it needs two shaded cells. That is sort of how I internally think about it, but it then makes everything look way nastier. I think if you try and say, okay, well there's a few ominoes, but the thing I want is to have two shaded cells in there, but that gets you your sort of extra degree of freedom, so if that works for you.
Can you repeat Coach's comment for the live stream?
Oh, sorry, the question was, can you think about this in a different way of saying, like, this just has to be shaded in this instance and that has to be shaded in this instance? And I said, yes, you could think about it that way if you want to keep the full degrees of freedom, or you can think about it as the, like, okay, this is a triomino, but it actually needs two shaded cells to meet all my degrees of freedom.
Okay. Earlier you were talking about if there was a rule set that it's implicit that there are no unshaded loops. And I have to tell you, it's Guide Arrow, and it's the best genre.
Oh, Guide Arrow is great. Yeah, yes, Guide Arrow is great. Yeah, so Guide Arrow definitely is this, and it is a great genre. Yeah, if you want to, if you've never used Puzzlink, by the way, you should absolutely go on Puzzlink. And at any point when you want to basically disappear for a week, pick a random genre on Puzzlink and start at the 1 difficulty and just go up. Or sometimes, actually, it's better to start at 2 because sometimes the one, so like if you look at Heyawake, for example, this is a great point to mention this. If you look at 1-star Heyawakes, because of the way Puzzlink rates difficulty, a lot of them are penalty theory puzzles, which seems quite counterintuitive. But what Puzzlink actually does for difficulty is it counts the number of cells in the grid and then counts the average time that someone who successfully solves the puzzle takes per cell in the grid. And so there are a few keywords there, such as who successfully solves, and then the amount of time. And so you can see how if you successfully solve a penalty theory puzzle, you might look at it and say, I can just fill in half the cells in the grid if I know what I'm doing. And if I don't know what I'm doing, well, then I'm not going to solve it, so my score's not going to count anyway. The 1 difficulty things, because it's automatic difficulty rating on Puzzlink, the ones are like half puzzles that are genuinely intro and half puzzles that have one silly trick that you might or might not know that only very good solvers are going to get. So that's why 2 sometimes is the sweet spot to start.
What could SudokuPad do to support these kinds of puzzles better, and should it?
It absolutely should, because I would rather do everything in SudokuPad if I possibly could. So the thing, Mark TechFan, actually, I think I was the precipitator of this, because I think I asked you to let me import Penpa puzzles, and then I think Mark volunteered to do it. So this Penpa importer is great, because if you're setting puzzles like this, you almost always are going to do it in Penpa, because it's this system that's designed to set puzzles of this sort. In terms of what additional tools there are, so my favorite thing about SudokuPad for all puzzles is the pen tool. And so most of the things that I would like are any extra functionality on the pen tool that lets me mark edges with something other than an X, say. So something that would let me like cycle through X and dot, for example, between 2 edges would be great. I'd love to be able to mark corners between 2 things as well. So for things like Star Battle especially, but for other genres as well, it's nice to be able to mark a 2x2 as being special in some way. So I'd like that as well. So basically, just a few extra, already the pen tool is great, and I don't want to do anything that makes it worse for people who are doing the things that it currently does, but there are a few extra kinds of mark that if they can be done or added without interfering and making other features worse, I'd love to have even more functionality on it, because it is, well, it's the reason, one of the reasons I really like SudokuPad.
You didn't mention weird answer checking.
Didn't mention weird answer checking.
Which is, right now, it only checks digits and stuff. So his question was, and should we? So I wonder if you think things like answer checking on shadeds or answer checking on lines, what your opinion of and should we for SudokuPad might be.
Answer check adds no value to my personal life. I will admit, sorry. I know plenty of people really like it. For me, if I think I've solved the puzzle, I'm either I have solved it and I'm happy, or it tells me I haven't, and I'm probably happier not knowing. So I'm not really that big on answer check. So for me, it doesn't really matter, but I know for a lot of people it does, and I know like the Penpa answer check is something I can never figure out. And honestly, like any of my Penpa puzzles that have answer check, it's because Vish or someone generously sent me a link with answer check because they were so frustrated that I could not figure it out.
I'm glad I'm not the only one who has a problem with that, because every time I have to go to the video and look at it. So as someone who doesn't solve many pencil puzzles, I'm not sure combining it with math was a good way to encourage me to solve pencil puzzles. But would you like to maybe give what some of your favorite pencil puzzle genres are and why we should solve pencil puzzles?
Why you should solve them. Okay, so every once in a while the Sudoku community goes through a phase where the setters, so every setter goes through a phase where they start off as a novice solver, and so then they're a novice setter, and their puzzles are beautiful. And then they get better as a solver, and what happens is then their setting gets significantly worse, because then they're able to understand these complicated ugly steps that if you watch my stream I complain about a lot. And so then they get better again once they realize, okay, I could put this step in my puzzle, but I also could not. And so the way it works sort of socially is that it tends to be that there are generations of setters every once in a while. So there's periods. And there was a particularly long one, which is when I got into pencil puzzles, where that's the phase that Sudoku is going through, where like a lot of the puzzles I do on LMD, I'm like, okay, I can't. And so that's one reason I find. And so I tend to sort of bounce back and forth between Sudoku and pencil puzzles. Clover would say Sudoku is a pencil puzzle. So I don't really that much distinguish between the two of them. But I will say if you're sick of Sudoku for whatever reason, it's a great variety because, well, if you think about it, Sudoku is one of the kinds of pencil puzzles. There are a billion other kinds. In terms of my personal favorite genres, I really like Shakona, which is a probably more niche genre that involves shading rectangles. I really like Compass, which is Basically, if you really like anything completely pathological, every compass puzzle is completely pathological. Because basically it always starts with, every compass puzzle starts with, well, I can almost prove this doesn't do that, but I guess there's technically a case where maybe it could like wrap around the entire grid twice and end up there. And if you ever think to yourself that in a compass puzzle, yeah, it does that. That's going to be the answer. And so that's very fun. I really like those as well. One reason why I recommend Heyawake, it's not so much that it's like my favorite genre to do sort of unchecked. However, there's a very good guide for it by Teal that I strongly recommend. I have a link to it on my Discord, but I'm happy if you DM me on Discord or whatever to give you a link, which sort of walks through the various phases of the kinds of deductions you could think about at the beginning. I really like any genre that has these guides. There's also one on Ubon, which I also perhaps recommend. I recommend the guide by Woofers and Jacob if you ever want to get into Ubon. Similar. If you know of guides of other genres, I'd love to have them, because I think it's very nice to have vocabulary for the deductions that I'm making in my head. Even if I've learned the deduction by sort of doing it myself, it sticks in my brain a lot easier by that. So things that are more common, Heyawake is more common, Yajlin is more common. You might find guides, although I've not seen one for Yajlin.
To sort of parrot a question that was asked earlier in one of our sessions, for those of us who are not on Discord, how would we be able to get access to these guides? Do you know if there's any resources for that?
Oh, that's a great question. Yeah, this is very much the thing earlier. That already got my brain turning of how can we convince Sven to have links to pencil puzzle genre guides in SudokuPad. Yeah, it would be great if someone had a website or something, wouldn't it? Yeah, but I don't know of a place that collects all these. Now, the thing that Woofers and Jacob do that's really great is all of their Ubon puzzles, they link to the guide. So if you come across one of their puzzles, it also has a link to the guide so that you can't miss it. With Heyawake or other things, I've not seen that. So it's a great question, but unfortunately, it's not a question I have a good answer to. Alrighty, well, thank you, everyone.